In the last screencast, I talked about basic collision theory, which just uses the average velocity of the system to say how frequently two molecules should collide per unit of time for a given concentration. And if 100% of the collisions give reactions, then the rate of reaction is going to be, or the rate of collisions will be a rate coefficient for reactions times the product of the concentrations. So we can say what the rate coefficient would be expected to be, this value k. However, in reality, most reactions require activation, and we need to have enough energy in that collision in order to allow the reaction to occur. So we can define a relative energy for a collision, which, just based on this being kinetic energy that's being transferred, the relative energy is given by the equivalent of 1/2 times the mass times the velocity, but because we're talking about two different particles, we have 1/2 times the reduced mass times the relative velocity squared. And the rate coefficient should depend on this energy. So the rate coefficient is going to be given by sigma, which is the reaction cross-section for a given relative energy multiplied by VR, which is the relative velocity. So in order to figure out what this function ought to be, we can consider the relevant energy for a given collision that occurs along a line joining the centers of mass of the particles. So to show what I mean, if we look on the next slide, if we're looking at a collision between this particle here and this particle here, notice they have different sizes, so they represent different quantities, we would expect that when they actually collide, it's when this particle has traveled to the point at which the distance from their center of mass to center of mass is equal to B max, but the distance from where they were traveling is equal to B, which is not necessarily equal to B max because there's a distribution of actual velocities, V sub r, the relative velocities. So based on this geometry, we can say what epsilon sub LC, which is the energy along the center of mass distances, should be compared to epsilon sub r, which is the relative energy just based on how the molecules are moving. So basically this straight line V sub r. So that should be 1/2 times mu times the velocity in the LC direction squared. And based on this geometry, we can show that that's given by epsilon r times 1 minus b squared over b max squared. So the value of this distance from the center of mass to center of mass along a straight line going from, in the direction that this particle is moving versus the maximum, which would be if they were barely touching. And we assume that a reaction occurs only if epsilon LC, that is the energy associated with the collision, is bigger than a critical value epsilon star. And so if we just insert epsilon star for epsilon LC, that gives us a critical value of B. So the reaction can only occur if B squared is less than or equal to B prime squared, which is equal to B max squared times 1 minus epsilon star over epsilon r, the relative energy of the system. So based on that, we can integrate radially over all possible values of B to get sigma, which is the effective reaction cross-section. We assume that the probability of epsilon r and B being 1 is equal to 1 for B less than B prime. So basically, if B is less than the critical value, then we assume that the reaction automatically occurs. So sigma, as a function of the relative energy, is given by the integral of the probability of having energy epsilon r and value of B equal to B times 2 pi B dB, because we're integrating over values of B. So this probability is equal to 1 as long as B is less than B prime, and it's equal to 0 if B is greater than B prime. So this probability just gets incorporated by integrating, instead of from 0 to infinity, from 0 to B prime. And so when we do that, what we end up with, and there's some algebra involved that I'm not going through in great detail, but we can show that sigma should actually be given by pi times b max squared times 1 minus epsilon star over epsilon r, where epsilon star is the critical energy and epsilon r is the relative energy based on kinetic theory. So based on this, we can now find the rate coefficient, k of t. So it should be given by the integral over all possible values of the relative energy of the system. That's what we're going to integrate over, of sigma, so that represents the cross-sectional collision value, times the relative velocity, times the probability density, so the probability of observing relative energy epsilon r. And this sigma term is given here, so it's what's written above. So we've got Bmax squared times 1 minus epsilon star over epsilon r. The relative velocity is given by this function, and we express it in terms of the relative energy, because that's what's of interest to us. And then this last set of terms is the probability density. So, fortunately, Houston worked out the value of this integral for us, because you can imagine it's somewhat tedious, and it involves some algebraic manipulation and simplification. But what you can show at the end of doing all this manipulation is that k at a given value of t for this particular model of the critical energy required for collisions is given by pi times Bmax squared times the average relative velocity of the system. And if you go back through the notes and look again, this is exactly the same as what we have for simple collision theory. So this is not including any sort of, I can't write, simple, my stylus doesn't make this easy. Simple collision theory gives us that value. And then the exponential of the opposite of epsilon star over kt is the modification. And this function is consistent with the Arrhenius temperature dependence, where the critical energy now is the activation energy. So this gives us, this theory is the minimal amount of detail required in order to be able to reproduce the Arrhenius temperature dependence. And it's usually as far as we need to go with collision theory in order to say that we have a model which is consistent with the Arrhenius temperature dependence and can make predictions about rate coefficients. And that's where we're going to stop. The only additional thing that we consider is that there's this steric factor p, which we expect to be less than 1, and we just multiply by that in our rate coefficient expression. This is meant to account for the fact that some reactions only occur if you have the right geometry, the right orientation of one molecule relative to another. Maybe there are lone pair electrons available on only one side of the molecule, and if the collision doesn't have those aligned, the reaction doesn't occur. So we expect it to be less than 1. You've already seen examples from what I talked about in class where p can be greater than 1. So basically that's when additional factors need to be considered beyond just what we're talking about here. But that's collision theory being modified so that it can account for the temperature dependence of reaction. And that's all I want to discuss as far as collision theory is concerned. Now another consideration is that, we made a very simple assumption when we said that we could just use this epsilon star value in collision theory and that would tell us all we need to know. It doesn't account for the molecular structure or the transition state. And in order to really account for what happens in a reaction, we need to consider the transition state. Now what this really refers to can be illustrated with a simple reaction. If we have a deuterium molecule reacting with a hydrogen molecule, a deuterium atom reacting with a hydrogen molecule to make DH plus a hydrogen atom, so basically we're exchanging one hydrogen between those two molecules, we can actually calculate exactly what the energy is as a function of two variables. So the distance between hydrogen atoms in the system and the distance between deuterium and hydrogen. So as this reaction proceeds, basically the distance between the two hydrogen atoms is initially small, but then once the exchange occurs, the distance between deuterium and hydrogen gets smaller and smaller, and then the distance between hydrogen and hydrogen increases because you basically exchange a hydrogen. And so if you look at this potential energy surface, you can take this three-dimensional surface and translate it as a contour plot, and what you find is that there's a point here which represents the minimum in the energy, or actually it's a maximum in the energy as you travel from reactants to products. So reactants are here. This is where we have a small HH distance and a large DH distance, so a deuterium atom and a hydrogen molecule. So we start here, we move along, the hydrogen atoms start to get further apart, but the deuterium is becoming closer. We reach a maximum as we travel along, and then we basically exchange the hydrogen, so the hydrogen-hydrogen distance increases and the deuterium-hydrogen distance stays the same. And this is actually a saddle point. So in the direction of the reaction path, it's a maximum, but perpendicular to it, it represents a minimum. And you can sort of see that here, that there's a minimum moving in this direction, and then there's a maximum in this direction. So it's sort of like sitting on a saddle. You've got a minimum in the direction where you'd be looking at the horse's head, and then where your legs go is a maximum. So that's what an activated complex corresponds to. And you can find these, and you can calculate their properties. So the next subject, which will be in the next set of slides, the next screencast, will be to talk about activated complex theory. And the idea here is that we take two simple steps where A and B make a transition state or an activated complex AB double dagger, and then that decomposes to make products. And we want to predict the rate of reaction based on that idea. And in order to understand this, you ought to understand something about statistical thermodynamics. So in this set of notes, I'm actually going to talk about that. So there's a primer about statistical thermodynamics that I'll go through first. And then based on that, and it's going to tell us where some of the terms come from, and then I'll come back and talk about activated complex theory. So that's what's coming next.